Hello, welcome to my Algorithms Huddles series. This is class number 2. Today we are going to look at using depth first search to solve the robot room cleaner problem. So this class is not an exhaustive treatment of the robot room cleaner problem. For those who have attended my live classes and workshops, you know how much I enjoy problem exploration for its own sake. And in the future, I will teach a few of those classes where we take a first principles look at a problem. Today is not that class. Today we are learning a particular solution to a particular problem. DFS being the solution and the problem is robot room cleaner. So let's get right into the problem. Here's a quick introduction to the problem. So we have a room which is in the form of a 2D grid, and it has these cells. Some cells are free, some have obstacles. All the free, let's make some obstacles here. So let's say these cells are blocked off. For example, all the free cells are connected. So the underlying graph is connected. So we don't have two or more disconnected pieces of this puzzle. So that's one assumption. The next assumption or consideration rather is to remember that we do not have direct access to this grid. Okay, so that's an aspect of this room part of robot room cleaner. So we don't have direct access to it. We have to discover this grid via the robot, which is the second part of our input. The more explicit part is the robot. So the robot is, let's say, starts off on an unspecified cell. It can face in any of the 4 directions: up, right, down, and left. And the robot has a fixed API. So the API of the robot, let's write it down here on the left, is 3 actions. So there is the right turn. Let me just adjust the camera a little bit. So there is the right turn. This makes the robot turn right by 90 degrees. This operation always succeeds. Then there is the action or operation called clean, which also is always successful, and what it does, it cleans the cell that the robot is currently on. If the cell has already been cleaned, I guess it'll clean it again. Okay. The last and the trickiest action that the robot can do is move. Now, move may return either true or false. When will it return true? When the cell that the robot is facing is existent, so it exists and is free. So when you invoke this action on the robot.move, it will attempt to move the robot to the cell that it's currently facing. If it's able to move there, it will do so. It will keep facing the same direction as it is right now, and it will return true. If it's not able to move because the cell is occupied, or the cell doesn't exist because you're at the boundary of the grid, then it's going to return false. Okay, so that's the robot. So we got the room. Some cells are free, some are not. All free cells are connected. There's no direct access to this grid. And then we got the robot with the 3 APIs. The problem is to design an algorithm that, when implemented, executes a particular sequence of these 3 commands: write, clean, and move, in such a way that ends up cleaning all the free cells of the grid. Okay, so very quickly to look at an example. So some of you know how I am a big enthusiast of slowing down at this stage of the problem solving process and taking a little bit extra time to say deeper, friendlier, longer hello to the problem. So if you are new to this problem at this point, you might want to pause this and look at this example and sort of hand solve it. Don't worry about the grid not being available. Just look at the robot's actions and how they might go. So for example, in this grid, we have a 3x3 grid, and so 9 cells, 4 of them are occupied, 5 of them are free and need to be cleaned. The robot is in cell that we're calling here A, facing up. So one possible journey that the robot might take is from A, it might go to C. So first clean A, it's facing C, then move to C, clean C, now it's facing D, now move to D, clean D, now it's facing nowhere, then take 2 right turns, do a 180-degree movement, come back to C, and now you're facing A. At this point, the robot could do 3 right turns to turn 270 degrees to face E, and then move to E, clean E, 1 more right turn, move to B, clean B. So that's just a way of spending some more time with the problem. So I encourage you, if you're brand new to this problem, to do this perhaps for maybe one more example, so you and the problem become good friends and you spend some time, okay? So now here what I've done is just put together officially everything we know about this problem right now. What is the input? What is the expected outcome? What are the assumptions? What are the considerations? So, take some time to go over this. I will just very quickly point out. So the input is, to be clear, the robot. The grid is an implicit part of the input. It's not explicitly provided to us. We know that the robot is on an unknown free cell of a 2D grid, okay? And we know the 3 ways we can move the robot, so that's part of the assumption. The outcome is make the robot clean all the free cells, okay? And the considerations, which we didn't talk about, so what are we trying to optimize here? Let's say we do not want to clean a cell twice and try not to visit a cell too many times. I know that's a little bit loose, but we're just getting started, so we don't have any strict considerations. Just try to visit a cell once, twice. Let's try and not visit it more than twice, not too many times. And turns, what about right turns? For now, let's not worry about the right turns. Do what you have to do. Let's assume that the turns are cheap. Okay, so we are going to write code that executes a sequence of robot commands that clean all the free cells. All right, so that was the problem. Now the particular solution to this problem that we are studying is applying DFS. So is DFS a fit? Well, the underlying graph is this undirected, fully connected graph. So there is very clearly a graph at play. So we could apply DFS to it. Each node has 4 or less neighbors, so it's not a humongous graph. It's not super dense. The density is sort of quite uniform. One thing about DFS that makes it a pretty decent fit for this problem is that DFS, as it unfolds on a graph, it produces a traceable walk. So whenever the DFS moves are go to a neighbor or come back to your caller, which is always your, there's always an edge connecting the 2 nodes that talk. So, and if this is something that is confusing to you, you might consider watching my other video called DFS Deconstructed, which is also a part of this series. In fact, it's the one that I did just before the robot, this particular one. So there we talk a little bit more about this traceable walk business. So this particular attribute of DFS does make it an interesting enough fit to try. So the robot can only move to an immediate neighbor, meaning that if we make the robot go over the free cells in a DFS way, we will never require the robot to jump across the cells. Okay, so it's a decent fit. Now that we have put that out of the way, let's look at a few considerations. If we are going to do DFS via the robot, then we need to switch gear to this robot and grid world out of, normally when we look at DFS, we are looking at an adjacency list or the root of a tree if it's a tree. Here we don't have the graph provided to us in any explicit way. So we need to take a pause and really think about what it would mean to make the robot do DFS. We have to make the robot copy or mirror all the DFS moves very carefully. Like go to the neighbor that you are facing, come back to the cell that you came from, which is return to your caller in the DFS recursive structure. Things like face the next neighbor. When you have an adjacency list, it's just a for loop that iterates over the list itself, and you always have the next neighbor ready when you start a new iteration of the for loop. Here, we are going to have to make the robot turn and then face the next neighbor. That's the only way we can discover the next neighbor and go there. So and so on. So this is one consideration to keep in mind. The second one is this graph can absolutely have cycles. So we are going to need the visited set of DFS. Now, if you remember this from your DFS learning, when the underlying graph has cycles, or if there is, even when it doesn't in some particular instances, again, you can see these details in the DFS deconstructed video, but the visited set is needed. It's an absolute must-have when there are cycles, let's just say. So for our purpose here, the graph can have cycles, so we need visited. What is visited? It is a data set that keeps track of all the cells or nodes of the graph that have already been visited by DFS. In order to mark a cell visited, we need to be able to uniquely identify each cell. And in order to know, so let's say we have a way to uniquely identify each cell. When I am doing DFS on a particular cell of the grid, the way the visited business actually unfolds is when I am about to go to a neighbor, I check if the neighbor is already visited. If it is, then I don't go there. That's the how of visited. The why is cycles, right? But the how is, this is how it unfolds. So in order for our robot to know the unique identity of the neighbor, the neighboring cell it's about to go to, it's also going to need to know its current direction, okay? So direction awareness is going to be needed in order to uniquely identify the facing neighbor. And unique identities for each cell are needed in order to make the visited set possible. So these are some considerations to think about. Now, in some online descriptions of the robot room cleaner problem, they will provide a 0, 1, 2-dimensional grid when they're explaining the problem. That is just for testing. So I don't want you to get sidetracked with that, or some people have reported to me that they found that confusing. The algorithm must guide the robot blindfolded using only the 3 commands. Now, we are applying depth first search to robot room cleaner to play with and to deepen our DFS familiarity and our knowledge, okay? Like I said earlier, if we wanted to play with robot room cleaner from scratch, that would be a slightly different exploration in the beginning. Okay, jumping right into the setup. Okay, this is, for this particular problem, I think this would be one mistake that someone might do, is to start writing the code. This problem has so many moving parts in terms of making the robot mirror the DFS moves that it's worth it to take some time to go over the setup of the problem before we jump into the final code, okay? So setup part 1 has two basic setups here. One, the question of the unique ID for each cell. Since we don't have direct access to the grid, we don't have an obvious way to uniquely identify each cell. So this is the technique we are going to use, and this is something that you'll see in other problems as well. So if this is the first time you're seeing it, I hope you're getting a chuckle out of it. It's a cute little clever thing. So the cell, the unspecified cell that the robot starts out on, let's call that cell 0, 0. Like here, let me highlight this so you know which one I'm talking about. So this, okay? So this is the 0, 0 cell. Now, any other cell in this grid, the unique identifier for any other cell, it's going to be a pair of 2 integers. The first one is the distance along the x-axis of this cell from the starting cell, and the second part of the pair is the distance along the y-axis from the starting cell. So as you can see here, cell A, it is 1 row above the starting cell, and it is 2 columns to the right of the starting cell. So the unique identifier for cell A is 1, 2. Now look at cell B, it is 3 rows below the starting cell, and it is 1 column to the right of the starting cell. So its identifier would be -3 and +1. Similarly, look at cell C. Here, it is 1 row below the starting cell and 4 columns to the left of the starting cell. So its unique identifier would be -1, -4. So that's our solution, our proposal for generating a unique ID for each cell. Now direction tracking. Direction tracking, this is what we are proposing. That we have 4 direction, let's call them direction, give them integer identifiers. You'll see in a minute why that helps. So up is 0, right is 1, down is 2, left is 3. Now it seems random enough, but it's not. So the way we have these directions as 0, 1, 2, 3, we have the concept of next direction. So if you look at the direction 0, the direction that is next is direction 1, which is 190-degree right turn away from 0. So the value of next direction is +1 modulo 4. And the meaning of next direction is 1 right turn, 190 degrees right turn from the current direction, okay? So that's the direction tracking. Next part of the setup. Now, we know that the way we end up using the visited set, the key way that we use the visited set is this. When DFS is executing on a cell, it's going to recurse on all the cell's neighbors. Just before it's about to recurse on a neighbor, it checks if the neighbor has already been visited. So in order to know that, we will need to know the unique identifier of a neighbor that we are facing before we consider going there. So this is a tiny little subroutine, and I'm going to highlight the subroutine bit here. Neighbor. Given the current location of the robot, which is x, y, and given the integer value of the current direction the robot is facing, which is dir, compute the unique ID of the neighbor that the robot is currently facing. So I've set it up a few different ways in case this is something you would want to spend a little more time with. You can pause here and look into it. I will just go through the subroutine, and you can look at this diagram over here, which explains it really well. So if the current direction is up, the neighbor you are facing is +1 to your row ID, and leave the column as it is. If the robot is facing down, you are doing -1 to your X value and leaving the Y value as it is. Similarly for right and left. So this is how we are going to compute the unique ID of the neighbor that the robot is facing, given the current direction, okay? So this is a subroutine that's gonna come in handy later. A little bit more setup. So another thing that DFS very naturally does when you look at the code for DFS using the adjacency list of the input graph is just iterating over all 4 of its neighbors. So given that the robot is on the cell XY and currently it's facing the direction dir, how do we iterate over all 4 neighbors? So this is the way you're going to see in the final code. Repeating 4 times the following 3 steps. Compute the current neighbor you are facing. Do whatever you want to do with that information. When you are done and you are in the next iteration of the for loop, take your robot, turn it 90 degrees to the right, and then compute the next direction by doing current direction plus 1 modulo 4. Now you are facing the next neighbor. Do whatever you want to do with that neighbor, reposition the robot the way it was when you're all done, then right turn, compute the next direction, now you're facing the next neighbor. If you do this 4 times, you would have faced all 4 neighbors one at a time, okay? So this is how we are going to iterate over all 4 of a cell's neighbors. Okay, so I taught a live class on this problem as part of my live class and workshop series. And this was a question that came up from a few people. So I wanted to take a moment to clarify it one more time. Why are we tracking the direction of the robot? Is it because we do not have direct access to the grid? We just saw that we can visit the 4 neighbors with 3 successive right turns. We can discover the 4 neighbors like that. We can even visit them. We don't need to track exactly what the direction is in order to just discover neighbors. So discovering is not the problem. Discovering can be done without knowing exactly what the direction is. The reason we need to know exactly what direction the robot is facing at all times is so we can identify the facing neighbor. Coming up with the unique ID of the neighbor we are facing is the reason we are tracking direction. Why do we need to identify it? Because we might not want to go there in order to avoid looping infinitely on account of the underlying graph having cycles, okay? So I just wanted to clarify that before we move further. Last bit of setup, okay? Mirroring DFS moves, not to take that part for granted. What are the DFS moves? Go to the neighbor. That's easy. If I'm facing the neighbor, all I have to do is robot.move and I go to the neighbor. Then what? Then you recurse. Do your DFS business at the neighbor. Okay, that we're gonna let the leap of faith of recursion take care of that. Then come back to your caller when you're all done. This is where I want you to pause and think, how do we reliably bring the robot back to its caller once it's done recursing? So let's say this was cell A and this is cell B, okay? DFS on A has now moved the robot to B, then called DFS on B. DFS on B finishes. Now I want to bring the robot back to A. How do I do that? Can I do that if I don't know the direction the robot is facing when it is all done with the DFS on B? And I think you can see that we can't. When the robot is done doing DFS on B, if it is facing right, I need to turn it 180 degrees and then move it back to A. If it is facing left, then it can just come back with a simple move, right? And if it is facing like here up, then it needs to do 3 right turns and then it's ready to come back to the collar. So I can't, right? We can't reliably bring the robot back if we don't know which direction it's facing. So let's do this. So this is actually not just set up towards the code, but this also helps us clarify the contract of our DFS calls. And again, those of you who have attended my classes, you know how excited I get about the clarity of the contract of a function before you write the function. I think you can avoid a lot of headache if you can take some time to really clarify the contract. So let's require this, okay? We're going to require this. When the DFS call on a particular cell is all done, the robot must face the same direction as it was facing just at the start of its DFS call. So I'm a cell, somebody sent the robot to me, and when they sent it to me, the robot was facing left. When I'm all done doing my business, my DFS business from me, then I must leave the robot exactly as it was before I started doing the DFS business, okay? So once we require that, then we can reliably bring it back. How? Turn 180 degrees and move, okay? So there we go. Now we are ready finally to at least put down the function header and the contract. So before we get to the recursive DFS bit, let's look at the outside bit. This one I'm highlighting here, which is robot roam cleaner main wrapper, because we need the main wrapper to declare and initialize the visited. So visited is going to be a hash set of integer pairs. And then we are going to do the first call to DFS with the starting cell being what we are calling 0, 0, and the direction as we are given in the problem specification is up. So this is basically X, this is Y, and this is direction. And this is our robot. And as you can see in the outer wrapper, RRC main, the only input we have is the robot. The discovery of the grid, the cleaning of the grid, everything has to be done via robot commands. So this is our seed call, and the main function, the main DFS function that we are concerned with is the one here, this one. So it has 5 inputs, the robot, the initial ID, the ID of the cell that the robot is currently in, which is XY, and the current direction the robot is facing, which is dir, and the visited set, okay? So that's the function header. What is the contract? The robot is on the cell XY, facing direction dir. Cell XY is dirty and free. I'm going to add that bit. And free. The job for this particular call to RRC is to clean all the dirty cells that are unvisited reachable from XY. All the dirty cells that can, dirty and free cells that can be reached from XY without hitting a visited cell. And if you this is the first time you are hearing this term, which, you know, I made it up, so you probably are, unless you've watched my DFS deconstructed video, then don't worry about it. It is just a slight nitpick on the contract. Okay, so the unvisited reachable means all the cells that are reachable from XY via unvisited cells only. Okay, when you're all done, leave the robot in the cell XY facing direction dir. This is the big bit. Leave the robot facing the same direction and face in the same cell. Cells with obstacles are non-existent. A dirty cell by definition exists. Okay, that's just a little definition. Okay, so this is our contract and this is our function header. If you have, so going back to this for a minute, at this point, we are ready to write the code, by the way. We could jump in and write the code in a few minutes now. We have all the setup. We have the outside wrapper, we have the function header, we have the contract, we have how to mirror the DFS moves, we know how to iterate over the 4 neighbors, we know how to compute the neighbor we are facing, and we know our setup for direction tracking and the unique ID for each cell. So we're ready. But if you're new to the problem, and this problem is highly clever and highly nuanced, on the surface, if you look at just the story of this solution, it's a pretty pedestrian application of DFS. But the actual implementation of it is extremely nuanced and clever, and that might not come across if you are learning this problem from some other source where someone is just giving you the code. The code is really simple in the end, or if someone is just explaining the various steps of the algorithm. I have heard from people about this problem saying that the code looks so simple and I do know DFS, but I'm having a hard time feeling confident that I truly do understand this solution. And what I would say, if you're feeling the same, is that you are having an appropriate response to the reality in front of you. This is highly nuanced and a highly clever setup, okay? So if this is the first time you're looking at this problem, and you are at this point where you've done the setup, you have the function header, you have the contract, you might want to just take a pause and hand execute the DFS as you intend now, with all the direction and neighbor setup, on an actual example before you jump into the code. If you want to do that, I do have something here in the slides for you to do that. You can pause and try to execute DFS on an actual example. So what is going on here? We have the input grid, right? Here, this is your input grid. It is a 3x3 grid. 4 of the cells have obstacles, and 5 cells are free. Okay, 0, 0, 0, 1, 0, -1, 1, -1, and 1, 0. The robot is right now situated in the middle cell, which we are, according to our terminology of unique identifiers, we are going to call that cell 0, 0, and the robot is facing up. Okay, so that's this part, 0, 0, and the initial facing direction, I have put a black outline around that direction. So if your initial direction is up, and you can look at this table underneath, which tells you if your initial direction is up, you are going to visit the neighbors in the following sequence. You're going to first visit the up neighbor, then the right neighbor, and then the down neighbor, and then the L neighbor. And that's the URDL here, okay? Up, right, down, left. If your initial direction was right, then you would go right, down, left, and up, right? So it just goes in a cycle with those 4 directions. So I've just put this table here to help do the by hand execution. So the starting point is XY is 0, 0, and the direction is up, and we are going to do URDL. So let's go up first. So I'm going to do that with a different color. So you're going to try the up neighbor first. So you're going to go to 1, 0, right? And this is going to be the first step of DFS. Now you are at 1, 0, and you're facing the direction up. You're always facing the direction from which you came, right? This up is related to this up. Again, this is going to try and navigate the neighbors. Now we are at 1, 0 here. Okay, maybe do a different color here. We are at 1, 0. We were at 0, 0. Now we're at 1, 0. From 1, 0, because it's currently facing up, we'll first try up. That's outside, doesn't exist, so that won't work. Then we are going to try right. So as you can see, 1, 0's right is 1, 1, which has an obstacle, so that move won't succeed. And then we are going to try down, which is your caller 0, 0, right? That's not going to work either. And eventually we are going to call left, which is 1. Something is wrong. Okay, let me fix this just 1 second. So this is not 1, 0. This is 1, negative 1. My bad. Okay. So that now you're at 1, negative 1 on account of going left from 1, 0, right? So that makes it the second move that you're going to make. From 1, 0, you go to 1, negative 1, and the robot is facing left, and that's why the left here is circled with the black. So hopefully you understand this kind of weird system I'm following. From here you will go to 0, 1, and from 0, negative 1, sorry, from 0, negative 1 you're going to return to 1, negative 1. From there you're going to return to 1, 0. From there you're going to return to 0, 0, and then you're going to go to 0, 1. So I highly recommend that if you are fairly new to this problem, or if you're having trouble feeling solidly situated with it at this point, this will be very helpful. Doing this hand solving and then going back to the setup, then attempting to write the code. So here's the final result of the hand execution. I've just made this slide for you to go over if you end up doing this. And I've also drawn up the DFS tree. So every DFS execution over a graph imposes a DFS tree on it, which can be really useful to look at. So I've put the DFS tree here. So this is some DFS lingo. Okay, so moving on. Now we're ready to write the code. So at this point, I would recommend that you pause and try to write the code yourself. We have everything in place at this point to write the code, okay? Here we go. There it is. So this part I'm not gonna go over. We've already gone over this, the part I'm highlighting right now. This is the outer wrapper, which initializes visited and then starts the root call. And this is our subroutine that we talked about earlier that computes the neighbor that the robot is facing, okay? So let's come back to the main code. Input the robot, different color, just as I'm going through this. Okay, so the input is the robot, X, Y, the current position, the current direction, and the visited data set, okay? First thing to do is clean this cell, right? You never call DFS on a cell if it has already been cleaned. That is the entire role of visited. So we can confidently clean this cell. We've never called DFS on it before. So the first order of business is to clean the cell. Next, we mark it visited. So we take our visited data structure and add XY to it. Set the current direction to the current direction, dir. Then basically we do what we talked about before 4 times, right? So first we compute the next neighbor, the facing neighbor. What is the neighbor that I'm facing? We have the subroutine. Then we're going to try and recurse on that neighbor. But before we recurse, we are going to check if it is already visited. If it's already visited, we don't go inside this if loop business. If it is not visited, which means it's not in our visited hash set, then we attempt to move to it. That might also fail if it has an obstacle or if it is a non-existent cell outside of the grid, then the move will fail. So these are 2 reasons to not recurse on a cell. Either we've already done it, or the cell doesn't exist, or the cell has an obstacle. So this if loop covers all those conditions and say none of that is true, which means it doesn't exist in visited and the move succeeded. When the move succeeds, you are already at that cell. So this is the big recursion, okay? Now you recurse on that cell. So as you can see, you have given it the ID of the neighbor you're facing, next X and next Y, and you've given it the direction it's currently facing. The move is not going to change its direction. and you're giving it the visited data set that now includes XY, because we did that above here. Okay. So now it does the recursion, and if it follows the contract, here's where you take the leap of faith of recursion and assume that it'll do everything right. That means when it's done, the robot is in next X, next Y, and it is facing current. Okay, so to reliably bring it back, we do the 180-degree turn, then we do the move back to the collar, and now this is the part that we didn't talk about earlier, reposition it. Okay, so let me draw this out a little bit here. So if this is cell A and this is cell B, the robot was facing this direction and then it went to B, okay? And then at B, it was facing this direction. It did its business at B. Now the business is completely done. Then we turned it 180 degrees, meaning now the robot looks like this. Then we did the move, okay? Now the robot looks like this. But when we called it, before we went to B, the robot looked like this, remember? And in order for us to iterate over our 4 neighbors, we need to reposition it exactly where it was. We can't take a right turn from here. We need to take it back, I take it back. Okay, we can do a right turn from here. Okay, that's gonna make it face up. We are on this sequence up here 4 times, needs to proceed properly. So we need to remove all evidence that we went to this neighbor. Okay, so then we need to reposition it to current direction, which would be, of course, just another 180 degrees. So now we have done the whole 360 and it's back to where it was. Okay, I'm gonna remove this. So hopefully that's clear that why these two, let me highlight them, why these two are needed. Okay, these two are needed to make this entire business that happened inside this if loop to be a no-op. Whether it happened or not, once you're outside the if loop, the robot is in next X, next Y, facing current direction. So now you can reliably turn it right, and now it's facing the next neighbor. Okay, this is how you can reliably face all 4 neighbors and not miss a neighbor by repeat a neighbor and stuff like that. So now it's simple, like we talked about before. Turn the robot to the right, it's facing the next neighbor, and update the current direction. So now we're ready to execute the loop again. And that's it, my friends. That's the DFS solution to the robot room cleaner problem. Now, as you can tell, it looks really simple, yes, but it's highly clever, highly nuanced code. So if you're feeling some discomfort, or if you're feeling like, whoa, these concepts are sort of mixing in my head, take some time, revisit it tomorrow. You know, the discomfort that you're feeling, it belongs. This is a slightly trippy problem, okay? And it doesn't come across. So I hope I've made that case, and I hope I have deepened your familiarity with depth first search. I have deepened a little bit of your familiarity with robot room cleaner type problems and depth first search on grids. So what next? Well, analysis plus, is this the best that we can do? You know, that's something we always ask in algorithm design. So let's go over the analysis. It's actually tricky. So move, at least it is for me, okay? I found, or maybe I find it marvelously tricky and I really relish in it. So tricky in a good way. So let's look at how many times the robot does all the 3 actions. So now the first one is move. How many times in our algorithm, the robot, how many times is it going to move? If you look at successful moves, the moves that are actually going to happen, that's going to be roughly 2 per cell. To be honest, it's going to be 2 times k minus 1 if, so I'm going to write this, 2k minus 1 if k is the number of free cells. So if you're interested in digging deeper into this, then this is how many successful moves we are going to have. Now, there will be up to 3 per node failed attempts, right? So that's, depends on the problem, depends on if you are solving this in in a real life situation at work, then you got to find out what is, are unsuccessful moves just as expensive as successful ones. But hopefully this analysis will help put all those pieces together and then make a call. Clean, we are sitting pretty, okay? We're cleaning every free cell exactly once when DFS is called on that cell. We never call DFS on a cell twice. Visited ensures that. Then how many right turns? This is a little bit tricky. I know we said right turns are not that big a deal, make as many as you like, but it's still good to know how many we're making. So I'd say roughly eight right turns per call in the worst case. 4 are to iterate over the 4 neighbors, the ones that are outside the if loop. And then there are 4 inside the if loop that we are counting along with the DFS call. So for each DFS, before DFS is called on me, I'm a cell, my caller had to do the 180-degree move and then 180 degrees. So those 4 right turns are just there to facilitate moving to me and then me returning the robot back to the caller. So that's 4 per call, and then 4 per call to iterate over the 4 neighbors. So that's 8 right turns per call. So that's kind of where we are in terms of analysis. Now, is this the best that we can do? Well, best how? Depends on what we mean by best. Are we trying to optimize the moves, the clean commands, or right turns, or all of it? So let's say moves, okay? So let's do moves. For now, we're already doing the optimum business in terms of clean and ignoring the right turn cost for now. Let's say, is our algorithm making the least possible number of moves in order to clean all the free cells? Well, no, because you can see in this example on the left, DFS is going to, let's say if it goes from A to B, right, and A to B, let's just say, okay, even if we do DFS in this sequence A, B, E, C, D, it's going to come back all the way to A, which is really frankly not needed in this case, because A, B, E, C, D, that sequence is our entire graph. There's nothing left. So the optimal number of moves for this will be move from A to B, that's 1, B to E, that's 2, E to C, that's 3, C to D, that's 4. So optimal number of moves will be just 4 moves. I think if there are K free cells, the optimal number of moves will be just K minus 1 moves. And DFS is definitely going to do 2 times K minus 1. So one way to look at it is, it's not bad. We are within a factor of 2 of the best possible number of moves. Another thing, we don't want to go too deep into this rabbit hole. It's a fun one though. I spent a few days there. Is that this problem, the robot room cleaner problem, it is a provably tricky problem if you want to optimize the moves, otherwise known as NP complete problem. So that should make us feel a little better, even better about our DFS solution, because it's not just that the DFS does not produce the least possible number of moves for every input graph, it's actually not, that algorithm doesn't exist. It's not possible unless P equals NP. So we are within a factor of 2. For the theoreticians who study approximation algorithms, it's not that impressive. They're probably working on something which is within a factor of 1.3 or something, but hey, we'll take 2, we are engineers. So I would say DFS not bad. Not the best, but since the best is provably tricky, we can feel pretty good. We can feel pretty good about our solution. Okay, extensions. In case you are where I was 2 weeks ago when I was preparing these slides and I thought I was done, but I thought, let me see different extensions of this problem. So if you are falling in love with the problem, or if you really feel compelled to know it even better and deeper and more, you can try these following extensions of the problem. The first one is the simplest one. What if the initial direction is unknown? So remember, we were told that the initial direction is facing up. What if we weren't told what the initial direction was? So this is kind of interesting. I think almost the same exact code would work. You just call the initial direction 0. If it is left, then we're calling left 0, and our setup, hopefully we can appreciate our setup even more now, is very clever. It's a highly nuanced setup. And by the way, I did not, it's not, I hope that you're not assuming that I took this problem and within 35 minutes, the golden amount of time you're given in software engineering interviews, I came up with this solution. No, I took my time to come up with the solution, then I checked online, then I dug deep into it, and then I prepared this class. So, if you want to test how well you know this solution, then you can try to code up what happens if the initial direction is not known. What I'm claiming is that you don't have to change anything. It'll work as it is. But you can test it. You're welcome to test it with a few test cases. I have not. This is just my prediction. Okay, second extension. You have direct access to the grid. Sometimes that can become a bit of a bigger distraction than it is to this problem's nuance and cleverness. The biggest distraction is not the fact that we do not have direct access to the grid. Our unique identifier system, I think, took care of it pretty well. So you'll be surprised to know that the code complexity is not going to change very much, even if you have direct access to the grid, even if you have the initial cell and direction to part of the input. So here's an extension for you to try. Direct access to the grid. You have the initial cell ID, you have the initial direction, and robot.move moves the robot to the cell it's facing. If the cell is non-existent or occupied, the robot will die. It'll break and die. So because you have direct access to the grid, do your own homework and try not to move the robot to some place that doesn't exist or is occupied. And of course, assume that the grid is 0, 1, where 0 is a free cell and 1 is an occupied cell. Okay, third extension. Back to the initial problem, the one we solved today. No cycles in the underlying graph. What then? Now that's a fun one, because all of a sudden, theoretically speaking, we do not need visited. Right? So if you have a cell and you have its 4 neighbors, right? So let's say it's facing right when DFS starts on it. So you can try to call DFS on the neighbor to your right. Then you're going to try to call DFS on the neighbor that's down. Then you're going to try and call the neighbor that's to your left, but that's your caller. Because your initial direction was right, that means you came from the cell to your left, right? So you were here on this neighbor facing right, the robot was facing right, and that's how the DFS call got originated at this cell. Okay, I hope this is not very confusing, so let me draw that again. So these are the 2 cells, right, A and B, and if the DFS starts off on B with the robot facing right, the point I'm making is that before it was on A facing right, because that's how we are setting up our DFS calls, that when you move, your direction doesn't change, right? So that means the moment you know the initial direction the robot is facing in B, you know that A is B's parent. Not the neighbor above, not the neighbor to the right, not the neighbor down, the neighbor that is 180 degrees from your current direction. So if you can just make sure that you don't call your parent back, because that could lead to an infinite loop between A and B, and that won't be because there's a cycle, that will be just because the edges are not directed. Just because this graph doesn't have cycles, it doesn't mean that it has clear parent-child relationships. So that would be the only thing we'd have to make sure of, that if I don't call my caller, so just skip the 100 and after 2 right turns, skip that neighbor, skip your 3rd neighbor, and then you'll be fine. You don't need visited then, because if there are no cycles, you'll never attempt to visit a cell again. and the code will look very simple. I did take time to write that code, so I'm just going to show it to you guys. It's beautifully simple. Hopefully it doesn't have any bugs in it. I did not actually test this. So as always, if you find any bugs or anything, please let me know. I'll try to superimpose some sort of correction on top of the slides in the video. But this is the code if the underlying graph does not have cycles. Okay, so that's a fun extension to try. It really helps us understand why we need visited. And the last extension, I just thought of it, I would say an hour ago. What if turning is expensive? What if a right turn is really expensive and you can move as much as you want? What then? I don't know. I think we're good for now. There's such a thing as too much fun. Okay, but I thought I would leave it there. Even I was done with the problem when I came to that extension. I was like, maybe another month, another year. Okay, but that's a wrap. Over and out, you guys. We are done. Thank you, and I'll see you in next class. Bye-bye.